Welcome to the Foundation Lectures on NST. My name is Herwig Mannaert, and in this third part we discuss the concept of emerging software element structures. Now, we have seen that we can treat or consider the software design cycle as a dynamic system. And in order to avoid dynamic instabilities in this design cycle, we need to deplete or damp the rippling of changes. Because these changes could ripple through the software structure, cause what we call combinatorial effects proportional to the size of the system and therefore lead to dynamic instabilities and unbounded changes. Now, if we want to avoid these combinatorial effects, and we demand that no such instabilities exist, we have derived a number of design principles which are in line with existing heuristics. And we have proven that adhering to these design principles is a necessary condition to avoid combinatorial effects or dynamic instabilities, not necessarily a sufficient condition. We have also reinterpreted the concepts of coupling and cohesion and came to the conclusion that it's in both concepts about the same thing. It's about coupling and it's about avoiding ripple effects. Both the high cohesion, which corresponds to coupling within modules, because changing pieces of software are confined together and therefore coupled into the same module, or coupling between modules, when changes in modules ripple through to other modules. So coupling is not just about counting arrows, it's about the nature of the connection. There's nothing wrong with a module which is used by thousands of other modules. It's called reuse actually, it should be something good. However, there is something wrong when that use, that coupling, is not version transparent and allows changes to ripple through. Now, we have also seen in these design principles that it's important that if we use simple data structures or data classes to represent data entities, or if you use simple processing functions or classes with a processing method to represent tasks or actions, processing actions, that we have to encapsulate them. We have to make sure that these classes, these structures, these processing functions are encapsulated properly, and if we change them, make new versions, that the interface doesn't change and these changes do not ripple through in a positive feedback mechanism. So we know that we have to encapsulate these basic principles, and what does it actually look like? Well, it's quite simple. For instance, for data classes representing data entities, we have to provide default constructors, getters and setters methods. And if we provide for processing actions, processing function or main method in a processing class, we just need to take care that the data entities which are passed are version transparent and that the interface is also version transparent. Now, another very important concept in software is cross-cutting concerns. And cross-cutting concerns are concerns that cut across your functional structure. That means you are confronted with it, you face it everywhere. That means if you have various functional entities like invoices, orders, payments, sensors, customers and stuff, they all face these same cross-cutting concerns because they cut right across your functional structure. For instance, persistency, access control, remote access, etc. Now, the other thing about cross-cutting concerns is that they cut right across your functional structure. You're faced with them everywhere, but also everyone is faced with them. Every software system is faced with these cross-cutting concerns like persistency, access control, etc. So basically, you have some standard solutions. Whether they are open source or commercial, you get standard solutions. And of course, you don't reinvent the wheel, but you want to use these standard solutions or frameworks that take care of these cross-cutting concerns. However, it's not because you use a standard solution or framework for access control that you're not confronted with the concern anymore. You have to connect to this framework. You have to tap into this framework, and that usually takes a couple of lines of code. For instance, you have to add a couple of lines of code in your class representing an invoice. A couple of lines of code may even be some simple annotations, but you need to connect them. Now, of course, separating concerns is also valid for separating cross-cutting concerns. This cross-cutting concerns is another change driver than the main class representing the data of an invoice. They have an independent life cycle because the invoice may be variable in its various attributes, but the solution you use may vary. You may use another solution after a while to take care of access control, or the interface, the API or the annotations change to interconnect to the access control framework. So this is a separate change driver and should be separated in a separate class, a separate software module, well encapsulated, in order that if you change the implementation of interconnecting, tapping into the framework for the cross-cutting concern, that change doesn't ripple through but remains confined or encapsulated within that class. Now, in general, of course, you would also have another cross-cutting concern like persistency. Once again, you would not do everything yourself, reinvent the wheel, but you would use an open source or a commercial framework that take care of persistency. But nevertheless, you have to do something yourself. You have to write a couple of lines of code, maybe a couple of annotations interconnecting to tapping into this framework. And these couple of lines of code are basically a change driver. They need to be separated in a separate class, encapsulated well that future implementations, changes, interface changes of this persistency framework will not ripple through your structure, so you need to separate them and encapsulate them in a separate class. For instance, an invoice data access class like an invoice access control class. Now, in general, how does that look like? Well, for instance, here on the left-hand side, you have a person details class just containing the data attributes of a person, like a name and an age and a function. And then at the right-hand side, you have a couple of lines of annotations tapping into the persistency framework of the Java Persistency API. Now, once again, here at the left, you see these couple of lines of code annotations tapping into this persistency solution based on the Java Persistency API. They cannot be part of the main class representing the data of a person. They should be separated and encapsulated in a separate class, encapsulating, isolating possible changes in the future of this framework. And the same is, for instance, valid for a transaction concern, where a certain class performing a creation of a person, you want to provide the transaction functionality, which is typically a cross-cutting concern provided by a framework, but tapping into that framework, interconnecting to that framework requires some dedicated lines of code which should be separated and well encapsulated in a separate class. And you can some other examples like here for remoting, where you have some Java naming and directory interface dependent code, or in a model view controller where you would have some, for instance, model view controller struts dependent lines, couple of lines of code. Once again, represented in shaded lines of code. Now, in general, you have multiple functional entities, you have a number of functional entities, and you have a number of cross-cutting concerns. So suppose, for instance, you have in this schematic drawing 3 functional entities, an order, an invoice, and a payment, and you have a number of cross-cutting concerns. For instance, you have the cross-cutting concern of persistency implemented through a persistency framework solution. Now, of course, that does not mean you don't have to do anything yourself. You still have to interconnect your functional entities with this framework. And you have to do that by adding a couple of lines of code and or annotations. And these couple of lines of code or annotations have to be separated into a separate class, well encapsulated, that future changes of this cross-cutting concern solution or the interface of this cross-cutting concern solution will not ripple through the rest of your structure. Of course, there are more cross-cutting concerns. Suppose we have, for instance, access control as well. Well, then, of course, this access control has to be used, tapped into, interconnected with by the various functional entities, order, invoice, payment, etc. And all these lines of code to interconnect, to tap into it, need to be separated, encapsulated in a separate class to connect. And suppose you want to provide remote access as well. Well, you have remote access frameworks, solutions that exist, but you have to tap into them, interconnect with them from your functional entities. And so for every one of your functional entities, order, invoice, payment, etc., you would need a couple of lines of code, and you would need to separate them in a separate class and encapsulate them and interconnect in that way to that solution. And so what you get is a whole set of functional entities in your system, and for every one of these functional entities, a set of cross-cutting concerns to which you have to connect. And so you get a number of classes centered around the central class representing the actual functional entity, like an invoice, an order, or a payment. And of course, you would also need then a standard interface class for every one of these functional entities that you can interact with between these functional entities without becoming technology dependent. So you need a technology agnostic interface. And this is what we call the emergence of elements, because for every functional entity, you don't only need a single software module, being the main class, implementing that functional entity, but you need a set of classes centered around this central class. Now, this implies that we have a more advanced transformation. Instead of transforming to implementing a functional entity, for instance, a data entity for an invoice, just in a single class representing the data and being well version transparent encapsulated, we need to implement it using several classes, a whole set of classes around this central main class, and providing an interface as well. And this set of classes we call an element. For a data entity, we talk of a data element, in this case, for instance, an invoice element. So instead of just transforming the entity in a single class, we transform it in a set of classes. The data entity is transformed not in a single data class or data structure, but in a collection of classes or structures in software modules. And the same is, of course, valid for a processing action. We don't have to just implement it, transform it into a single class with a processing method, well encapsulated, version transparent. No, we have to provide a number of classes around this central class, taking care of the interconnection with the tapping into the various solutions of the cross-cutting concerns, providing a technology agnostic interface. And this set of classes we call an element, in this case a task element, or more specifically a send invoice element. Now we remember that the basic transformation, where we just transformed every functional entity in a single software module or class, data class, or processing class, that one of the great problems was if we would apply changes on the left, we would not only have the transformation of that change into software, but we would also have positive feedback due to ripples of changes, where we would have to adapt those functions that actually create or instantiate the data entity, because the interface of the creation or instantiation of the data entity would have changed and would have impacted other software modules. Now, in this more advanced transformation, we transform every functional entity into a set of classes, properly encapsulated, taking care of the various cross-cutting concerns, and we transform them into a set of classes, data element set of classes for the data entities, task element set of classes for the task entities. And when we now apply changes, we might have to apply multiple changes to the software, but they would be confined to that element, encapsulated within that element, and the changes will not ripple through. The element structures will take care that the changes do not ripple through, and therefore the changes do not generate a positive feedback, do not generate a combinatorial effect, and we don't have an instability, we don't have a propagation of changes proportional to the size of the system, which may become unbounded if the system grows. Therefore, what are normalized systems elements? Well, normalized systems elements are element structures around central classes that implement functional entities like data or actions or tasks. But these central classes are surrounded by a whole structures, a set of other classes to interconnect with the various solutions of the cross-cutting concerns. And normalized systems theory defines 5 types of elements, and those types of elements are aligned with a very basic software concept, the same basic concept of software which date back to the von Neumann architecture and haven't changed in 70 years. Because what software basically do is represent data. We had data variables and structures, and now we have data elements. Software contains instructions and functions doing actions. We have therefore task elements. We have flow elements to orchestrate the control flow of the various actions and tasks. We have connector elements similar to input-output commands to allow for input of output, and we have trigger elements to offer a periodic clock-like control to drive certain processes and flows. So we start from the same basic concepts which have been there for decades and decades in the processor architectures, in all the software programming language. But what we do is every one of these basic concepts, we surround the basic implementation with a number of peripheral implementation classes interconnecting to the various cross-cutting concerns and providing encapsulation to avoid ripples going through due to changes. Now, it seems obvious and clear that this will create a lot of structure, a lot of repetitive structure in the software implementation, so it seems obvious to use code generation techniques to create instances of these recurrent element structures, because the class structures of the various classes of the invoice data element and the order data element and the payment data element and the sensor payment element, they all will look quite similar. So it seems obvious to use code generation techniques. But because we have such basic and elementary structures, and they are so recurrent and so deterministic in nature, they just serve to interconnect to the various cross-cutting concern solutions, we refer to this quite deterministic process for code generation as expansion, and the code generators we call expanders. So if we represent it in a very schematic way, at the top you see a number of functional entities, functional data entities like invoice, order, functional action or task entities like creation of an invoice, processing of an order, sending of an invoice. And then we would have template structures for the various types of elements, data elements, task elements, flow elements, connector elements, trigger elements. And so the software code base at the lower end of the drawing consists of a number of instantiations of these element templates, a number of instantiations or recurrent structure implementing these various elements. And we come back to that later. We just want to finish here with a little bit of interpretation and explanation of what is this kind of element actually. Well, it is basically integrating, making at a very fine-grained level structures for every functional entity connecting with the various cross-cutting concerns. So if you would look, for instance, at construction of houses, your functional entities are the bricks or the stones or the building blocks, and the cross-cutting concerns would be water and electricity and heating and stuff. And so you would want to make, in this regard, in this respect, you would want to make building blocks, basic building blocks, like brick-like building blocks, that take care of this integration, that do not only provide you with some structure, with some protection, with some isolation, with some main structure to carry the weight, the support of the core, but you would also interconnect with the various utilities or cross-cutting concerns. You would provide pipes for water, for sanitary water, for heating water maybe. You would provide pipes for electricity, for instance, even provide sockets. And of course, you would make this interconnection with the cross-cutting concern frameworks in a version transparent or encapsulated way. The pipe for the electricity would be able to carry copper and later optical fiber, etc. It would not be tied to a specific implementation for your electricity. The pipes for the heating system would be able to carry any fluid that you would use for various heating systems. Other types of fluids, other kind of central heating systems, but it would just carry a fluid. So you would incorporate into the structure the interconnection with the various utilities or cross-cutting concerns, and you would do it in a version transparent or encapsulated way. Now, of course, we've been saying that for many years, but now you start seeing more and more integration of interconnection with cross-cutting concerns at a fine-grained modular level. If you see, for instance, the solar tiles of Tesla, you see that those tiles actually are just ordinary tiles which you can use to make a roof, but they provide solar electricity, photovoltaic functionality. You would see that people are starting to propose plastic roads, and they say this could be a revolution, because every time you have a problem with communication connections, you have a problem with electricity connection, you have a problem with draining water with sewers, etc. You have to drill open into the roads. Now, if you would have prefabricated pieces of road integrating the connection with the various cross-cutting concerns like electricity, like communication, like water, like gas, it would be far easier to do maintenance works on roads. It would be far easier to upgrade your central utilities. You see in the New Dragon spacecraft of SpaceX that the solar panels are all over the place, that you don't have external solar panels, but that you have embedded photovoltaic functionality. And you also see examples, for instance, in containerized data centers, where you have a container where you can store servers, IT servers, but at the same time you have all the cross-cutting concerns being taken care of within the container through diesel generators, through batteries, through air conditioning systems, etc. So, of course, you can always contact me if you have any further remarks or questions, and I thank you.